today we're going to be looking at trends in ionization energies. So by the end of this tutorial, hopefully you'll be able to define ionization energy and write equations, explain the trend in ionization energies across a period, and predict the group number based on successive ionization energy data. Okay, so let's move on. So the first objective is to define ionization energy and write equations. So the definition for first ionization energy is it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions with a +1 charge. Okay, so the important bits here are it's 1 mole of electrons to form 1 mole of gaseous ions with a +1 charge. The equation for this, so we can just use any atom we want. So I'm just going to use the letter A to represent an atom. It has to be gas, so you need the state symbol G, and it will form A plus G plus E minus. So the common mistakes people make is they forget to put the G, the gas, in state symbols, and they forget to put the electron as an E minus. Okay, so this is what it would look like. If that was sodium, you would just replace the A with sodium, Na, etc. Okay. Second ionization energy, it's pretty much an identical definition, except this time we're saying that it's the energy required to remove 1 mole of electrons from 1 mole of gaseous ions with a +1 charge to form 1 mole of gaseous ions with a +2 charge. Okay, so the difference this time is you're removing it from a +1 charge. So the second ionization energy removes the electron, another electron, but you're still only removing 1 electron. So the equation would be this. So A plus goes to A2 plus E minus. Don't forget the gas state symbols. Really important, it's A plus for the second ionization energy. Third ionization energy, you would obviously start with A2 plus and it would form A3 plus, etc. You're only ever removing 1 electron when we're talking about these ionization energies. So if you were talking about first and second, then there would be 2 different equations. Okay, so we're going to have a look at electron configurations recap. Last video we looked at how you did electron configurations in terms of 1s2, 2s2, etc., main shells and subshells. Just thought we'd do a really quick recap. So electrons are arranged in main shells, which are numbered 1, 2, 3 and 4, and then they're arranged in subshells, which are S, P, D and F. The S subshell holds 2 electrons in 1 orbital. An orbital is an area where electrons exist, and an orbital can hold a pair of electrons with upspin and with downspin. An S subshell has 1 orbital, so it can hold 2 electrons. A P subshell holds 6 electrons. It has 3 P orbitals, which would hold 3 electrons. 3 electron pairs, which means 6 electrons in total, and again they would fill like that. The D subshell can hold 10, it has 5 orbitals, and there's lots more detail in the previous video if you want to have a proper recap on how to do electron configuration. Okay, so the second objective, we're going to look at how we explain the trend in ionization energies across a period. So if this was an exam question, with the command word explain, you need to give reasons why. It would be sufficient to say what the trend is and then go into the details. So I've picked period 3 just to look at here. We've got the elements along the x-axis along the bottom, and then we've got the energy along the y-axis in kilojoules per mole. Okay, so there's 3 things that we're going to look at as we go through this. First of all, we're going to talk about the general trend. We're going to look at specific trends, and there's 2 deviations from it. So the first thing that we're going to think about is the general trend across all of these ionization energies across period 3, and that general trend is that they increase. So the general trend is they go up, they increase. Okay, there are 2 deviations from this increase. There is a deviation here for aluminium, it decreases, and there is a deviation for sulfur here, it also decreases. Okay, but generally all of the rest of them increase. So let's look at in more detail and let's think about saying why. So the general increase across a period, this can be explained due to electrons and the nucleus. So as you go across the period, so from sodium to argon, the number of protons in the nucleus, so protons in the nucleus increase. You have more protons, okay? Therefore, there is a stronger attraction, attraction between the outer electron that you're trying to remove and the nucleus. Because there's a stronger attraction, the electron is harder to remove, therefore requires more energy. The other really important point is when we're dealing with period 3, so we've got the nucleus in the middle. I'm just going to go on to a new slide here. So we've got the nucleus in the middle. So we've got the nucleus in the middle, which has got a positive charge. Because we're talking about period 3, we're talking about the third main shell. Okay, so these are representing electron shells, perhaps as you would have seen them at GCSE. This is the nucleus, which is positive. You've got electrons in the first main shell, the second main shell. These would be S and P electrons rather. And then you've got the third main shell here. They all exhibit the same shielding. So the shielding is the effect from the nucleus to the outer electron. So this here is the outer electron. The shielding is what these inner electrons are doing. So these inner electrons are blocking off the nuclear charge coming from the nucleus to the outer electron. As all the electrons are going into the same main principal shell, they all experience the same shielding. Okay? Okay, so now we're going to look at the deviations. So there is a small dip between magnesium and aluminium. Okay, so we need to think about why that might be. And we'll think about that in terms of electron configurations. So the sodium, because it's in period 3, has a 3s1 configuration. Magnesium has 3s2, just looking at the outer shell electrons here. And the aluminium has a 3p1 configuration. Okay, it obviously has 3s2, 3p1. Okay, so what's happened is we're moving from an S subshell, specifically the 3s subshell, to the 3p subshell. Because the aluminium electron has now entered the 3p subshell, it's slightly higher in energy, which means it's a little bit further from the nucleus, which makes it slightly easier to remove. Okay, so the 3p electron has entered a new subshell, which means it's slightly easier to remove, so it requires less energy. So less energy is needed. Okay, and that's because it's going from the 3s subshell to the 3p. If it was period 4 ionization energies, then you would need to say 4s to 4p, and if you were talking about the second period, it's 2s to 2p. It's always the same. I've seen in mark schemes that they're looking now for more detail. So if they are specifically talking about, say for example, magnesium and aluminium, and to explain that dip, be specific and say the 3s subshell and the 3p subshell. Don't just say S and P. Okay, there is another small dip between phosphorus and sulfur. Okay, so this small dip again can be explained in terms of electron configuration. So we just looked at the electron configurations up to aluminium. Silicon is obviously going to have a 3s2, 3p2. Phosphorus 3s2, 3p3, and then sulfur 3s2, 3p4. So what's going on here between the 3s2, 3p3 and the 3s2, 3p4? For that, we need to think about orbitals, okay, and how electrons are in the orbitals. So if you remember in the previous video, we talked about how electrons will enter the orbitals separately, and then they will start to pair up. So the 3p3 electrons will go in all unpaired like this. The 3p4 electron will start to pair up. So it starts to pair up with the other electrons in an orbital. Now, because electrons are now going into the same orbital, as both electrons are negative, they both have opposite spin, one spinning up and one spinning down. That's going to create repulsion. Okay, and there is repulsion in the 3p subshell for period 3. That repulsion makes it slightly easier to remove the electron from the 3p4 than it is from the 3p3. Okay, so that's really important. A little analogy I sometimes give as to why electrons do this. So sometimes I imagine orbitals as being like seats on a bus. You know, you've got a bus with double seats. Well, people, when you go onto a bus, you'll go for an empty seat. You won't sit next to anyone. If there's a spare seat, and electrons are the same. They won't go next to each other unless there's nowhere else to sit. So if you go in, and then once you're paired up, then there'll be that slight bit of repulsion. Okay, so to summarize, there are three key things that we need to get across. The first point is that there is a general increase across a period, okay? And the reason for that general increase is simply because there are more protons. Because there are more protons, there is a greater nuclear charge. Another really important thing is the elements have the same shielding. They've got the same electron configurations of inner electrons. So therefore, they experience a stronger attraction from the nucleus to the outer electrons. It's important that it is the outer electron that we're talking about, okay? So it's a general increase because there's more protons, therefore more positive charge. The elements have the same shielding, so there's not less or more shielding. They've got the same configuration of electrons between the outer electrons and the nucleus, so therefore there is stronger attraction. The second point is to explain the first dip. The first dip is between aluminium and magnesium in period 3. Okay, it's between group 2 and group 3, and that is because the outer electron is now in the 3p subshell, which is higher in energy. Therefore, there's weaker nuclear attraction and less energy needed to remove that electron. If you were talking about period 2 trends, then it's the 2p subshell. If you were talking about period 4, it's the 4p. The pattern is repeated regardless of which period you're talking about. It's just we're looking specifically here at period 3. The second dip that we need to explain is to do with sulfur being lower than P. So sulfur is lower than phosphorus because now the outer electrons in the 3p orbital begin to pair up. They repel, and therefore less energy is needed to remove. Okay, so the key thing here is they're pairing up, they're repelling, and it's in the 3p orbital. Okay, so that's what we need to say. Similarly to previously, if you're talking about period 2, it's the 2p orbitals are beginning to pair up, or if it's the 4p. Okay, so predict the group number based on successive ionization energy data. Okay, so successive ionization energy is removing further electrons, so it's removing 1 electron, 2 electrons, 3 electrons, 4 electrons, so on and so forth. As you remove more electrons, it's going to always get harder. So the first electron is going to be the easiest electron to remove because you're removing an electron from an atom which is overall neutral. Once that electron's removed, there are now fewer electrons than protons. So removing a second electron is going to be harder because there is a stronger attraction between the nucleus and the electrons that are remaining. All electrons are going to be harder from there on because of that same reason. However, there is always going to be one electron that is particularly hard to remove, and that is the electron where you've gone into a new main shell. So if we're thinking about what happens, so electrons are being removed and then they're being removed from the next main shell, which is lower in energy and therefore closer to the nucleus. Okay, so if you think about that in terms of GCSE, so if you were to draw out electron structures like you did at GCSE, so we've got the nucleus here positive in the middle, you've got electrons here, this would be the first shell, this would be the second shell, okay? So you remove this electron, that's going to be quite easy relatively to remove. The first electron in this example would be relatively easy. The next electron is going to be significantly harder because it's now in a new main shell. Because it's in this new main shell here, it's closer to the nucleus, so therefore there's a big jump. So with this, you're looking for a big jump. So where is the big jump in this example here? So 1000 to 2251, 36361, they're all going up by about the same amounts, going up similarly. Whoa, holy moly, that's a big old jump there. So from 8496 to 27,107 kilojoules, that means the 7th electron is much harder to remove than the 6th electron. So think about that. So we're removing 1, 2, 3, 4, 5, 6 electrons with a sort of steady increase, and then all of a sudden the 7th electron is really hard to remove. That is because there must be 6 electrons in the outer shell, the main shell, and then the 7th electron has gone into a brand new shell. So therefore it is in group 6. Which element is in group 6 of the periodic table, period 3? It's sulfur. Let's have a look at this again. In terms of the graph, you can see it's much easier when you plot them on a graph. There is a huge jump here between 6 and 7, therefore it is in the 6th group, because it's the 6th group which is easier. It's the 7th which is a big jump. So if they gave you this data in an exam and said explain which group it's in, you would say it's in group 6, and the reason for that is because there is a big jump in ionization energy, 6 to 7. So therefore it must be in group 6. Okay, I'll leave this for a moment. You have a look at that and see if you can work out which period 3 element that could be. And if I show you the graph, does that make it any easier? Where is the big jump? So there's a similar increase between these two. Broadly speaking, those have similar. So there is a big jump between the 2nd and the 3rd. So we're looking at something which must be in group 2, because it's the 2nd and the 3rd where is the big jump. So between the 2nd and the 3rd, it is magnesium in period 3. Which period 2 element could this be? Okay, so looking at this data, they all seem pretty puzzling indeed. Let's look at the graph. That's not made things easier either. Maybe if we looked at the 9th, look at that big jump. So the huge jump here is between the 8th and the 9th electron. So we're removing 8 electrons with what you would expect to be the general increase, and then the 9th is much bigger. What is in group 8? Well, they're the noble gases, or group 0. So this one would be neon. So what am I saying here? So if they only give you 8, and there's a very similar increase in ionization energies as you go from 1st to 8th, then you can probably conclude that it's going to be in group 0 or group 8 if you're calling it by the old school group numbers. So it's going to probably be a noble gas. Bit of a harder one to do that. Okay, and then you can see clearly on the graph there is a huge jump here as you go from 8th to 9th. So that just confirms to us that is group 0. Okay, so we've looked at trends in ionisation energies. So we've defined ionisation energies and written equations including state symbols. We've explained the trends in ionisation energies across a period. We've looked at period 3, but exactly the same explanations will be applicable to periods 2, 4, etc. And hopefully we can predict the group number based on successive ionisation energy data. Okay, thank you very much for listening. I hope that was helpful. I'll see you next time.